Hi, everyone. Thank you for providing us this opportunity to present our work here today. I am Avishri Khare, and I am here with Hed Shah, and we would be talking about our ESoC project called ML4Land. We would first like to thank our amazing set of mentors from ECMWF for their constant support and guidance throughout our ESOC journey. Thank you, Esperanza, Julia, for the constant support as well. Okay, so let's get started. Next slide, please. Yeah, so this is the agenda for our presentation today. We'll start by motivating you about the problem that we are trying to solve, all the way through to what we actually achieved and where the project is headed to in the future. Next slide, please. Okay, so what is ML4Land? The core idea behind ML4Land is to understand important land surface cover characteristics. And the characteristic that we focus on here is the radiative skin temperature, commonly known as the land surface temperature or LST in short. So why is LST important? The answer to that lies in recent research, which suggests that LST is heavily correlated with several other important physical phenomena, including land use patterns and heating patterns of the earth. And so if we have a model that can accurately predict land surface temperature, that would also provide us valuable insights on these phenomena. And I'm sure most of us would love to see that. Next slide, please. Okay, so how does ML4Land do this? So we wish to build a model that can predict satellite variables by using input variables from the model world. So the satellite variable in our case was the land surface temperature that we get from the NASA MODIS satellite. And the input variables are ERA5 reanalysis variables, including 2-meter temperature, dew point temperature, total precipitation, and so on. The objective here is twofold. Firstly, we obviously wish to have a model that can very accurately predict land surface temperature. And we also want to see how this compares against existing models of LST. The model that we use for benchmarking is ERA5 reanalysis variable called skin temperature. And we wish to see how our model is better or worse compared to this ERA5 skin temperature. We also want to understand where ERA5 skin temperature is currently lacking and how that can be improved by using our model as a post-processing step. The second important objective is to find a consistent set of variables that can help in determining land surface temperature. If we have a consistent set, we are sure to head towards robustness, and that would also help us understand if our model is using the right physical intuition for making predictions of land surface temperature. So as you can see here, it's a very simple thing that a tool does. It takes in ERA5 input variables and attempts to output very accurate land surface temperature predictions. Next slide, please. Right. So here is the roadmap for our project. We have a 4-step process, the first 2 of which were completed before the mid-evaluation. And after the mid-evaluation, we focused on regional estimation. Here, instead of having individual sites or individual points for which we predict land surface temperature, we instead have large regions for which we wish to accurately predict land surface temperature. So the challenge here was to extend our model from being a point-wise model to also understanding characteristics of an entire region. The 4th step here, which is global estimation, is something that we wish to continue in the future as a part of this project. So this presentation would mostly be focusing on the regional estimation and the results that we got from that phase. Next slide, please. Okay, so here is the pipeline for regional estimation. We model this entire process as a regression problem, uh, primarily because land surface temperature is a real valued variable, and we compare that against some modest ground truth land surface temperature values. There are three important components in this pipeline. We have the data, the model, and the metrics used for training the model. So let's start with the data. We consider two important regions here, and two diverse regions indeed. The first region would be in and around United Kingdom, so roughly covering the entire United Kingdom. And the second region would be parts of Southern Europe and some parts of Northern Africa. For these two regions, we took the data from 2000 to 2021, and these are the ERA5 input variables that I was mentioning earlier. This data is divided into two sets. We take the years from 2000 to 2018 as the training set, and the years from 2019 to 2021 as the testing set. For the point estimation pipeline, we considered the months of February and August. However, for the regional estimation pipeline, we only looked at data from the month of February to understand how well our model can work for a given month. The second part of the pipeline is the model, which varies based on the learning algorithm used. We experimented with several ML algorithms, including linear regression, random forest, neural networks, and so on. And the final part of the pipeline was the metrics. We used mean squared error, where we compare our predicted land surface values, land surface temperature values, to the LST values that we get from the NASA MODIS satellite. We also have our benchmark, which is the ERA5 skin temperature values, and we see how well our model is performing as opposed to that. So the pipeline has an ML model which takes in some data and compares that with NASA MODIS data till it can churn out accurate LST predictions. I would now like to call Heath to continue with more details on our work.
Thank you, Avishri. So moving on, next slide, please. So as Avishri was mentioning for the past few slides, we take ERA5 reanalysis variables as an input points for our input data. So we consider two different sets of variables. So these variables would make up two different independent sets. Right? So the first set, we take two different sets of variables. So both of the sets are given over here on our screen. So the first set and second set have some common variables which are mentioned. So from TP to wind speed, there are some common variables which we include. And on top of that, we have some different sets of variables. So for the first set, there are T2M and D2M, which is the 2-meter temperature and 2-meter dew point temperature. And for the second set, we have rad, which is the radiation from the Earth's surface, as an added variable which we consider. So there is a simple reason as to why we take these two different sets of variables. So the first set contains T2M and D2M, which are model outputs, which are directly influencing the skin temperature. So this is in a way sort of the model output, which is the skin temperature or land surface temperature, and it has been it's like a proxy to that particular data. And we don't always want that to be used in our model, because that is in a way sort of cheating for our model and sort of getting the output before actually trying to predict the output. And in set B, we have radiation, which is not a part of the model. So in this particular set, the model has to understand and come up with the predictions entirely on its own. So these are the two sets of variables which we sort of consider. Moving on for the next slide, we'll now begin to show results of our models, which Avishri was also talking about, and we'll show results on two regions. So the first one is the UK region, and the second one would be the Southern Europe and the Upper African region. So for the UK region, we come up with, so there are four sort of diagrams that you see on your screen. So on the top right is the MODIS LST data. So that is the ground truth data that we get from the NASA MODIS land surface temperature dataset. And on the bottom right, we see ERA5 skin temperature, which is again from the ERA5 dataset which we have. So you see there are some white regions in the NASA MODIS data. So the land surface temperature dataset is only available on the land part, as the name suggests. And it is also missing for the places where there are cloudy regions. So that's why the lower UK region is missing some data in that particular day. So it could be possible that in some other day that the data is available for that particular region. But for this particular day, it's missing because there was some cloud cover over that particular region in the UK. So coming to the results of our own model, so we have just shown one model for each set, which was the best performing model for us. So for the set A, we have this sort of diagram, and for the set B, we have this sort of predicted a map. So we see that we get an improvement of around 2 Kelvin for both of the cases. So it's quite close. It's 2 Kelvin for both of the sets, and it's around 35% improvement on 35% improvement against ERA5. So one thing to note is that we are using random forest model for both of these sets to predict our outputs. So, and again, now we see what are the top 5 variables, because this is what will determine what is going on inside the random forest model. And we see that some set of variables are common between the both of the sets for the prediction, and T2M D2M is getting replaced by RAD. So this actually shows, and this is like physically also explainable as to why these variables are affecting the prediction of land surface temperature more. So moving on to the next slide, we perform a similar sort of an experiment here again for the Southern Europe region. And we again see better performance compared to the ERA5 skin temperature. So we see around 1 Kelvin improvement for set A and 0.6 Kelvin improvement for set B. So this turns around 21% and 13% respectively for set A and set B. So some more interesting things to note from these set of experiments is our models, our random forest models, are able to capture the heating patterns of Africa in a way better manner than what ERA5 is actually seeing. So you are seeing yellow patches over here in our predictions, which is sort of missing in the ERA5 skin temperature region. And the variables again are coming out to be consistent for both the sets. So next slide, please. So there were some challenges also that we faced along while performing this sort of experiments. So the first one was trusting the LST values that we get from the NASA MODIS dataset. So in the first UK experiment, we were getting around 6 RMSE score for the ERA5 SKT temperature. So it was puzzling to us that why we were getting such high RMSE score. So what we did was we took only the good quality data using the quality check flag on the MODIS LST dataset, and we sort of reduced our dataset because we are now only considering the good quality dataset. So now we saw around 23% improvement in the RMSE score for ERA5 skin temperature. But again, this was not changing the performance of our model, so which shows that our models are robust to these good quality or bad quality data. And it actually shows how effective our models are in this particular case. The second challenge was scaling. So right now we showed results on 2 smaller regions again from the European region. And this is not actually entire global scale. So scaling is still an issue for us. So that's why we are only considering smaller heterogeneous regions of Europe as of now, but we do plan to scale it to global region, global or continental regions in the future. And the third challenge is ERA5 is an hourly dataset. Like it gives you values for each and every hour, whereas MODIS is for a daily basis, and also sometimes the data is missing for some regions, like due to cloudy cover or due to bad quality data and stuff like that. So this is again a challenge, and we are trying to impute or aggregate values or trying to use neighboring values to impute the values. which are missing and sort of giving us more data in that way. Next slide, please. So finally, we conclude and give an outline as to what we plan to do next. So to conclude, our models, machine learning models, are able to understand patterns in the data set, in the data that we are trying to provide, and are also being robust in the sense that it is robust to the bad quality data and fluctuations which are getting predicted in the data set itself. And a consistent set of variables are turning up as the most important features for predicting the LST values. And these values are physically explainable to what could be the values. And as a future work, as even Avishri has talked about, we would like to extend it to a global scale and continental scale, and sort of experiment with neural networks which capture local spatial relationships between different points which are there, which we haven't done till now. So this is it from our side. Thank you so much for having us.
Thank you, Avishri, and thank you, Hit. It was great. Yeah, thank you for your presentation and very impressive results of your project. I have a question regarding, you showed the results now for the random forest outcomes. But at the beginning, you said that you actually also want to compare different machine learning models. Did you also already implement different models and you chose random forest? Or this would be now one of the next steps, as you pointed out in the future work, that you would like to also investigate more into neural networks with spatial dependencies?
So for now, we have experimented with some of the models which Avishri has talked about, like logistic regression, decision trees and stuff. But random forest was the best performing model for us till now. So that is what we have shown the results as of now. And we would be sort of experimenting more with neural networks in the upcoming days. So that is the plan as of now.
Okay. And what challenges do you see when you now want to go to a global scale?
The biggest challenge would be that of memory, because we don't have enough memory on conventional systems to handle data of that scale. And what we then have to do is to shift to better machines. So far we were only working on local machines, and we would definitely love to take advantage of the Veka Cloud credits that are offered. And we'll also be using several batching techniques so that we reduce the amount of data that is present in the memory at a given instance of time. So we'll have to just look at how efficiently we can churn out data from the storage to the RAM. And that seems to be the only concern here.
Okay. And so I understood you will continue working together with your ESoC mentors even after today.
Yes.
Yeah. Okay. So that's already great to hear. And again, it was great, or it is great to have you as part of ECMWF Summer of Weather Code this year. And thanks again for your presentation today and for being with us today.
Thank you so much.
Thank you so much.